Okay, so thank you very much for coming on a Friday. I know it's a short week. I mean, probably a lot of professors are at conferences and stuff like that. But we have a very interesting guest. I actually met at ICSP a few months ago. His name is Julio Deride. He's in California Davis. He's a PhD student there. He's finishing. And he's going to be presenting today his work on Lopsided approximation for solving equilibrium problems. Thank you very much for coming.
Okay. Okay, so first of all, thank you for the invitation, for Rodrigo, for inviting me to give this talk about my work that I've been developing for my dissertation. It's a joint work. Today I'm going to show you, I would say it's half of my dissertation. And it's a joint work with Professor Roger Wetz, which is my advisor in the University of California, Davis, with Alejandro Jofre, which was my former advisor in Universidad de Chile, and also we are still collaborating in this job, and Yoyo Fan and Soumya Guo from the Department of Engineering in the University of California, Davis, that presented me a very interesting problem that we're going to see by the end of the talk. So let's start giving you some structure of my talk. I'm going to talk about equilibrium problems, and I'm going to formulate the equilibrium problems as maximum optimization problems. This is a new family of optimization problems which are based on these primal dual Lagrangian functions, and we're going to try to characterize equilibrium problems as maximum problems. Then I'm going to develop a theory which we're going to use for approximating this type of, this family of problems, these maximum problems. We're going to use a proper concept of convergence, which we're going to call lopsided convergence. Finally, in order to solve this approximation, approximated problems, I'm going to talk about non-concave duality and how we're going to end up with finally with a solution for our equilibrium problems. And by the end, I'm going to talk about 3 specific problems that we have solved with this new technology. So first of all, let me talk about what is an equilibrium problem. And an equilibrium problem is basically whenever we have a situation where multiple agents are interacting between each other, and they're going to try to get each of their decisions are going to affect the decisions of the other agents. And they have to come up with, or the outcome of this interaction has to be at some equilibrium. There are several problems that follows into this category. For example, we have a fixed points equilibrium problems, fixed point problems, which can be interpreted as equilibrium problems. We have variational inequalities that can be used for to model this type of situations where we have multiple agents taking decisions, and we can formulate, let's say, an extended variational inequality with a first-order condition, first-order conditions for each agent's problems. We have the well-known example of non-cooperative games. For example, Nash equilibrium problems is a very well-known example of equilibrium problems where each agent interacts and their decisions affect the other decisions of the players. And the ones that I've been focused is the Walras equilibrium problem, where the decisions of each agent don't affect directly the other agents in the economy, but they affect the prices, and the prices is the mechanism how they interact. So as you can see, we have several problems of equilibrium problems that we can study. And well, the most important thing of an equilibrium problem is that we have a set of different individuals, and they're taking decisions separately, and they affect each other. So let me start with an example, with a basic example of a Walras equilibrium problem, or the classical Arrow-Devereux model, which is an exchange economy. I have a finite set of agents. Each agent this is an economy where I have a finite number of agents. Each agent has initial endowment of goods. Let's say in the general case, general assumptions can be made about this initial endowment. Let's say I have a market of apples, bananas, and each agent has a positive amount of apples and bananas, and they want to trade these apples and bananas. Each of these agents have a utility function, which is going to be described by U of A. Well, let's say this utility function is going to be upper semi-continuous, it's going to be concave, but in our setting, these conditions can be relaxed somehow just to be upper semi-continuous and just have quasi-concave. But let's say that it's concave. Actually, in the general theory, this utility function is sometimes strongly concave, and it has to be continuous, and actually it has to be differentiable or twice differentiable. Yes.
So what is L? Is it a finite set?
Oh, yeah. L is a finite set, or is the amount of goods that are going to be traded. So the utility function, each agent has a utility function that for each good it's going to reflect the preferences of these agents among goods. I'm going to call CA the domain of this utility function, which is going to be a subset of the space of goods RL, and it's going to be called the survival set. In the general case, well, let's say that CA is the minimum, or is where this UA is finite, right? Because at some, it can have some utility levels that, sorry, there's a typo there. It should be are extended, where this thing is plus infinity, where this is unfeasible. So that's why I'm using the CA. Sorry, there's a typo there. Yeah, so this is a survival set, actually, when the consumption of this agent can happen. For each price, we're going to define a price system P, which is going to be non-zero, actually has to be positive. And in this reduced model, we can make the assumption that this price actually lies in the simplex of RL. Why is that? Because we have the budget constraint of each agent, which is going to say that each agent can be traded a bundle of good X at the price P, such that his consumption does not exceed the price of his initial endowment. So each agent come to this economy with initial endowment, they trade it, and they decide their optimal consumption. So the agent problem, how can I skip this? Okay. Thank you. So the agent's problems is going to be maximize this utility function, U of A of X, over the survival set, such that the budget constraint is satisfied. So I'm not spending more in my consumption than the amount of money, if you want, I have available, and I have to maximize my utility function. I'm putting here an argmax, and I'm using one of these solutions. Let's say that in the classical assumptions of the economy, or in the economic literature, this can be a single value set, and this is going to be just a function of each price. But in the general case, it can be it can have several values, and I'm taking one argmax. So with this, with the consumption of each agent, which I'm going to call CA at a price level P, I'm going to define the excess supply functions, which is going to be the aggregate excess supply, meaning that is the difference between all the goods that are available, the sum over all the agents of the initial endowments, minus the aggregate demand, which is the sum over all the individual's demand. And I'm going to say that an equilibrium is going to be a price P bar in the simplex, such that this excess supply is going to be positive or non-negative. in the sense that in the general case, people ask for equality, but that requires some stronger assumptions in general. I just want to satisfy the demand of the agent at the price level P. This only guarantee that I satisfy the demand. I'm not requiring that both of them has to be equal. How can I solve this? Well, classically, in the economics literature, they use a fixed point algorithm applying Scarf's idea or a triangulation idea. Or in general, the general methods to solve this type of problems are I divided in this family of methods, which are simplicial methods, basically a combinatorial argument based on the Sperner's lemma, which is the Scarf algorithm. So you are enumerating the vertex of the simplex, and then you're going to triangulate on them. The tâtonnement methods, which you came up with a dynamical system for the price. Let's say first ordinary differential equation on the price P, such that they move towards the direction of the excess demand, and then you try to solve it with ODE's method. You have homotopy methods that you try to solve an economy which is simpler, and then try to make this solution converge to the complicated economy or to the complete economy. And you have new methods which people are trying to formulate this as an interior point methods or augmented Lagrangian, and the one that I'm going to show is this new Walrasian method. Why I'm trying to came up with a new method, with a new methodology to solve these problems, because all of the previous methods described, first of all, they require stronger assumptions on the utility functions or on the availability of goods, and in general, even when they are satisfied, for example, the simplicial methods are too slow for a big size economy. So you cannot find economies that actually reflect how an economy works that can be solved with simplicial methods. The same with the tâtonnement methods and homotopy methods, which requires a smooth behavior of the excess supply function that you see is composed by an Rmax, which requires a lot of smoothness of the utility functions. And finally, the interior point methods and the augmented Lagrangian, well, they are both based in the same concept, so they require a lot of smoothness on the parameters of this economy. So let's see how this Maxim formulation is going to help us to solve this problem with some relaxed assumption and try to see how we're going to solve these problems. So first of all, let me give you some setting about the Maxim optimization problems. I'm going to define the finite value by bivariate functions from Rn to Rm, which are going to be the functions that are finite values, and define over this cross product of C cross D. So settings that are, so it's a cross product in the domain. I'm going to define a Maxim point. X bar is going to be a Maxim of a finite value function if I'm maximizing in the first argument of the function the family of the infimum over the second variable. You can see that this is, you can relate this with a max-min type of setting. If you have in mind some Lagrangian function, you can think of this as a Lagrangian that I'm maximizing on the dual or minimizing on the primal. But this is more general in the sense that I'm just interested in the max on the first variable and only in the inf on the second. So I'm not interested if you want to put this Maxim family of functions in some mindset. I'm not interested in doing the full duality at some point. I'm just interested in max inf. And this is why I'm going to be interested in lopsided convergence, in the sense that I'm going to ask for a stronger sense of convergence, of course, when I need the max, and a weaker sense of convergence when I need the inf. So this is going to be a maximum point. An approximate maximum point is going to be a point such that the value of the sub-inf is going to be at an epsilon distance of this evaluation. An approximate maximum point is going to be a point that is close to the maximum, but on the value. For this family of problems, I'm not interested in the proximity of the equilibrium point. I'm interested in the proximity of the values of the function. So that is something that we have to keep in mind, in the sense that whenever I set an approximate maximum point, I'm not in a neighborhood of a maximum point. I'm going to be a point that is close. When I evaluate this sub-inf, I'm going to be close to the sub-inf of the original function. And why is that important? Because whenever I'm talking about the equilibrium points, I'm just interested in satisfy the equilibrium condition by an epsilon level of tolerance. Sorry, by an epsilon level of tolerance. So I want to be close to an equilibrium in the evaluation and not in the in a neighborhood of the equilibrium as it is. So if we go back to our equilibrium problems, we can define this by function, which we're going to call the Walrasian function, which is going to be defined from the delta, from the simplex cross the simplex, taking real values, and for each prices, which I'm going to call P and Q, I'm going to define the W of P and Q as the dot product between Q and the excess supply function evaluated at P. I'm trying to come up with a function that characterizes the equilibrium from the Arrow-Debreu economy. So in this case, this can look somehow tricky if you study this problem. So how can I come up with a function? If you study the first papers of Arrow and Debreu, they have a very similar inclusion function in their paper. So this W function is trying to price the excess supply at the price P with a different Q. And we're going to try the different combinations. We're going to say that an equilibrium point or P bar is going to be an equilibrium point if a P bar or a price P bar is going to be an R maximum of this W PQ function. This is interesting because whenever you see the maximum of this W, P, and Q, I'm going to set, if you look at this P bar and you evaluate, you're going to have the W of P bar is going to be that the infimum over all Q of the excess supply of P bar has to be maximized over all the price. It's the maximum, right? So I have the infimum over all the Q over, in this case, if you see the dot product of Q and S of P, Q lies on the delta. It's a price which lies on the delta. So whenever I took the infimum over Q, whenever I took this infimum over Q of delta, this infimum is going to give me the component that is most imbalanced, where the excess supply is less negative, if you want. I'm going to take this infimum over Q of S of P. This is the dot product of Q times S of P. Whenever I take the infimum of that, it's going to give me the market that is most imbalanced. And then I'm going to push up, taking the maximum. I'm going to take the infimum, and then I'm going to take the market, the prices that goes up, that take up this market. So this interpretation of this P bar being the maximum is an equilibrium point of P bar. After you think after you think about it, you can realize that actually it's going to do this equilibrium. It's going to take the most imbalance and increase the price, or try to move the price to increase the excess supplies of that price. So our equilibrium problem now is to find a price P bar that maximizes this the function that for each P it assigns the infimum over Q of WPQ. So how we are going to solve this problem? we're going to introduce, we want to construct an algorithm that solves this type of problems. So we need to look for a proper notion of approximation of this family of maximum optimization problems. And this is a novel concept that was developed in the 80s, but it has the wrong definition, so it was reformulated a couple of years ago, and it's going to be the concept of lopsided functions. And in the general setting, what we have is that we have a maximum optimization problem over a bifunction f, and we want to find a price or a point maximum belonging to this maximum optimization problem. We want to solve a simpler problem or approximated problems that are easier to compute, and we want that this family of approximating problems converges to the original optimization problem, to the original maximum. So, of course, if the epsilon nu is going to 0, I want that the x nu converges to x, and now I need to ask what are the properties, or what is the correct convergence that I need to apply of these bivariate functions of f nu. And this is the concept of lopsided convergence. And in this case, I'm going to talk about lopsided convergence, y-tight or ancillary tight, which is a particular case when we have some compactness on the domain. But in general, whenever I want to approximate the maximum optimization problems, I'm going to look for lopsided convergence. I'm not going to show you exactly what is the concept of lopsided convergence, just because it's a lot of epsilon subsequences and sequences. But the idea is to take the idea of the approximation of max-min problems when you have the topology of hypoepi convergence, and you try to weaken the assumptions of the inf of the mean and replace it by the inf. So it's a weaker concept in order to get the convergence of the maximizers, of the maximum optimizers. If there's any question, we can review the concept of lopsided convergence by the end of the talk, but I don't think it's relevant at this point. A couple of main results of our convergence theorems taken by the work of Joffre and Wetz of 2014. So if I have a sequence of bifunction converging lopsided y-tight, first of all, if I have a sequence of epsilon approximating maximum points of f nu, and I have a cluster point, then this cluster point is going to be an epsilon maximum point. So if I fix the tolerance level epsilon, and I solve these approximated problems of f nu, then the cluster point is going to be an epsilon level. Actually, if I take the epsilon level going to 0, the cluster point of this approximating sequence is going to be a maximum point of the original problem. And actually, we have the converse in the sense that if I have a maximum point of the original problem, I can find a sequence of epsilon nu going to 0 and x nu of the approximating problem such that I have the convergence. So I have the full characterization of epsilon nu maximum problems for the approximated f nu and the maximum problems for the original function. So now that we have the correct setting of convergence, I'm going to discuss how we're going to actually construct this approximating sequence. Usually, these equilibrium problems are not the main problem is that they are not concave. As they are not concave, one can expect some difficulties if you are trying to solve these equilibrium problems as variational inequalities, where the operator is not monotone, or even you can find some problems with the continuity of the excess supply function. So what we're going to try, how we're going to construct this approximation is that we're going to take the non-concave duality. We are assuming, or we're going to get a setting that our original function, which is going to be, our original problem is to find x bar that maximizes this family of infimum of f of x and y, of infimum over y, and we're going to assume that this family of function is non-concave. So if this is the value function of this family of optimization problems, we're going to have a duality gap. And with this duality gap, we're going to try to use the non-concave duality in the sense that we want to construct the max mean such that I can get into this duality gap. So we're going to use this non-concave duality. And how we're going to use this? Well, we're going to, instead of using linear dual functionals, we're going to use augmented functionals with an augmenting function, which are going to call sigma, which is going to be a convex function with a minimum at 0, and it's going to get steeper and steeper. It will not matter how not concave this thing is. I can find the parameters such that with any of these green functions, which these parabolas, I'm going to be able to reach the duality gap. I'm going to be able to break this duality gap that was produced by the linear approximation, and I'm going to use this quadratic or non-linear approximation. Why I want to have duality? Because I want that the max equals to the mean in the value. I don't care, as I mentioned before, I don't care about the, let's say, in general, I don't care about the value of the slope. I just want to evaluate, I just want to have the equality on the values. So with this, I'm going to call an augmenting function, sigma, which is a proper lower semi-continuous convex with a unique minimum at 0 with a value 0. So it's going to be like a parabola, if you want to keep that in mind. But it can be a norm function or any function that satisfies this. And we're going to define the augmented Walrasian or the augmented approximation, if you want, as the infimum, or it's going to be the convolution of the original function and this regularizing function. This all comes from the non-concave duality. It's a little bit, well, you have to work the algebra, but this is the final form that you get when you try to write the duality setting for these nonlinear functions. So if you see, this is not a regularization of the original function. If you see in this graph, this is the graph of the value function for the perturbation problems. If you want, if I have a Lagrangian or a pre-dual of this original problem, I'm going to try to access to the duality scheme for that pre-dual. It's not that I'm adding like a quadratic term on the variable x or on the variable y. I'm adding a term in the dual. Sorry. I'm dualizing in the pre-dual of this thing or on this problem, and then I'm going to try to take the minimum. And at the end, I end up with an infimum over the second variable in Q, if you want, and this convex conjugate of this sigma function. So now that I have this, sorry. I'm not sure if I put it, but obviously once I have this approximation constructed, this W tilde of nu is going to convert to lopsided y type to the W original. And that thing is going to be, finally, the problem that I'm going to solve is going to be the maxinf of this problem, of this family of problem. Eventually, this family of maxinf approximation of this W tilde nu are not going to be simpler than the original one, but I'm guaranteed that if I solve this family of problems, I'm going to have a solution at the end. And that is the importance of this. That is one of the importance of this work, is that we are guaranteed to converge to equilibrium problem. So how the algorithm work? Well, we have two sequences of scalars, R nu converging to infinity, epsilon nu converging to 0, and at some point we need to find a sequence of epsilon nu maxinf of this augmented Walrasian function. At any iteration, we're going to separate the overall iteration in two phases. The phase one is going to be the infimum over Q. If you remember this W, the W is going to be a convex function, is a convex optimization over a delta simplex, so it's going to be easier to solve, and actually we solve it with Gurobi. And on phase two, we're going to use the maximization problem, and this is the most complicated part of the algorithm. If you see this function W tilde of n+1 of P and Q nu plus 1, if you see the form of W tilde as a function of Q, is going to be an infimum for any fixed Q. This is going to be the infimum over W, and you can forget about the rest by the moment, but this function as a function of P is going to be the X supply as P. So it's going to be still a complicated function to maximize. So we're going to use a solver that actually use a quadratic, sequentially quadratic approximation with a trust region method and without using the derivatives, which is Bobiqua, and it's a library developed by Powell. So we're trying to use the less information that we can about the second order properties of this function. We are not assuming that it's C2, or we are not using any complicated approximation for that. And as we know, well, our augmented Walrasian lopsided convergence, so we expect that the P nu or the epsilon nu maxinf optimization problems converge into an equilibrium point. So the first, well, we try the first example. We have the scarf example. This was a small economy with 10 goods, 5 agents, which were heterogeneous agents. We have a CES utility function, initial endowments that are strictly positive. We use a self-dual augmenting function, and we use this sequence of R nus, and this is one of the iterations that we get. This example was solved within 10 minutes, so it was kind of fast for the parameters of equilibrium problems. If you try to solve any fixed points with problems with the 10 variables, well, actually this is 10 prices that you have to fix, but you have a lot of other variables. If you see the extended formulation of this problem, you have that each agent has to take an X, a vector X, so you have 50 variables of consumption, so you have 50 consumption decision plus the 10 prices, so it's like a 60 value. It's a fixed point of 60 variables. And it was robust. Whenever we changed the initial point, we got a convergence of this with this algorithm. So in the last minutes, I'm going to talk about the 3 applications. One is the extension of the Walras equilibrium problem. I want to talk about the infrastructure planning problem and a general equilibrium with financial markets, which are 3 equilibrium problems that we solved with this new technology. First of all, the natural extension of a Walras equilibrium problem is to add uncertainty. We add another stage, and we add this transformation matrix, if you want, where we can decide to save some goods on the first stage by this matrix T0 of A, T0 for agent A, and we save a Y amount of goods of that. And on the second period, I have a stochastic return of TA of psi times Y. So I have like an input-output matrices, But all of this occurs in the markets of goods. I don't have contracts. I can use these technologies. These agents has some technology available, so they can save some goods with this T0, and then they have an uncertain return at the second stage. So I have L goods here. I can save T0, Y goods here, and then I have an uncertain return at the second stage. Yes? Yes. Here?
Yeah.
Yeah, for every C. For every psi in the capital psi, you have one of these constraints.
But that's a discrete set.
Yes. Yeah, we're working on on the discrete case by the time. Yes. The C, each of, yeah, we can assume that all of them are convex.
I'm thinking in the application to the financial market.
Let me think. I guess you can.
It's like a restriction over buying some specific good in some future state.
I guess you can work with that in the sense that whenever you can see this problem as a stochastic program with recourse with two-stage. The only constraint that I have is whenever I do the simple recourse, I have a non-empty set, let's say convex in that case, in order to guarantee feasibility of this set, of this problem. So whenever I try to do this relatively simply recurse of, as we call it in the paper, ample survivability constraint, in the sense that each agent can survive and this problem has a solution. So eventually you can have some non-convexities, but when you have to take the intersection of all of them, if you want, then you have convexity. So for each agent, we're going to solve this problem. We're going to use some stochastic optimization technique to solve it. We actually use a progressive hedging algorithm to solve the agent's problem. So for every price P, we're going to find the optimal consumption and the optimal saving policy, if you want, with this transformation matrix. And we're going to define the excess supply as the difference between the goods that are available plus the goods that are going to be consumed. And again, the equilibrium price is going to be a price P bar such that the excess supply is going to be non-negative. So if you so for every price P, whenever I have to get the C0 and 6i of P, I'm going to use the progressive edging to solve the agent's problem. So I have a really, well, this problem is a huge problem if you start multiplying all of the decision variables of the agent times the price times the scenarios, and adding the prices, the size of this problem grows really big. And still we can define a Walrasian, and we can define a P-bar, which is going to be an equilibrium point if and only if it's going to be a maximum point of this W of this Walrasian function. And we can prove that this Walrasian function actually converges tight lobe to W tilde. So we have the convergence of the approximating P. What type of problems did we solve? Well, we solve an economy with 7 goods. Well, you can interpret as a skilled, unskilled job, leisure consumption, risk-free bond, and 2 stocks. We have 5 agents, and we have 9 possible scenarios. So if you see the problem here, just the prices are going to be of dimension 70, plus you have to multiply that for 5 agents. I will have 7 decision variables for consumption, plus other 7 decision variables for the transformation matrices. So this problem It's a really complicated one in the sense that if you want to solve the equilibrium problems at once, I think you cannot solve it on MATLAB, for example. So we ran this this algorithm. It took about 12 hours of running in a laptop machine. I haven't tried anything of this in any cluster computing. So on a laptop, it took 12 hours approximately, and we get the convergence of the prices. The second example is the electrical vehicle charging station infrastructure problem, which is my joint work with Professor Fan and Samuel Guo, one of her students. And in this case, I will have a network, let's say that traffic equilibrium network here, and the red dots are going to be investors that has to make a two-stage decision. First of all, they have to decide capacity at the planning stage, and then they have to decide generation at the second stage. So they're going to invest in one of each nodes. What they have is that you have origin destination. You have the drivers go from this point to this point, and they have to load at some point. They are driving electrical vehicles, and they have to invest on where they're going to put the charging station in order to optimize the investment from the investor point of view. So each of these investors is going to invest, for example, in that blue node, they're going to invest in this capacity, and this driver is going to pass on this road. So we are trying to model this situation. The investor problem, these are the equations, but basically we have we are maximizing somehow the profit, which is going to be rho, which is the price that is charged at each station S, times the generation at this station, minus the generation cost, and the overall, we have to subtract the capital cost of investment. So I'm going to invest. The investor is going to decide the capacity at each node, and it's going to decide the generation at the second stage. I'm showing you the deterministic version. We are working on the stochastic version, and this is the one that is published. We have some preliminary results for the stochastic problem, but in that case, we have some stochasticity on the second stage, meaning the generation and the price in the second stage is going to be stochastic. So our constraint is going to be the generation cannot exceed the capacity, and I have to have positive generation and capacity. This is the investor problem. How we're going to decide the traffic equilibrium? Well, we're going to use a combined distribution assignment. It's going to be, let's say, an independent system operator, which is going to, if you want, maximize the utility of the drivers or the society. And in some sense, it's going to, or minimize, let's say, a function that is going to depend on the travel time, local attractiveness, charging capacities, and charging costs. And we're going to have this constraint, which is basically the network flow balance. I'm not going to go into details. I don't have time for that. But let's say that all of these constraints are going to be the feasibility on the network. And this is the form of the utility function where you can see that there's some parameters, beta there, that can be, well, we use different values for the parameter beta to see how the solution changes. For this market, we can define the excess supply S at each price rho star. We're going to define the equilibrium where the generation is equals to the total consumption, if you want, or the total load at each node. And we still can introduce the Walrasian function of this. When I first got this problem, they were stuck trying to solve the equilibrium problem, and I saw this problem in the seminar, and I said, oh, we can try this this new technology, and it fit almost perfectly. We have to assume some perfect competition on the market of investors, but it's not a dramatic assumption. And sorry, there's a typo there. There's a minus sign there. So we define this Walrasian function, and we solve it for the Sioux-Falls network. Let me show you this. This was a really interesting case that we solved. We have to solve 12 prices, but we have to solve this traffic network, which was a really big problem. We were able to solve it in about the same amount of the big problem. It was like 14 hours. The interesting thing is that it was very sensitive to the parameters beta. This one was for a beta, or let's say one parameter of the utility function that didn't consider the charging time. So if this independent system operator that do the traffic assignment does not consider the time for charging, the investors just collapse all the investment in two nodes. The big one that is there and the other one that is down there. So we have some clustering behavior depending on the parameters of the utility function, which can be interpreted as a signal for the regulator whenever you have to design this type of things that you have to keep in mind, for example, the utility function of the agents. Last thing. Do I have time? Okay. Let's discuss the last equilibrium problems that we solve. We have a general equilibrium with financial markets, the typical GEI model, where we're going to have heterogeneous finite agents, I. We're going to have L+1 goods, or let's say L goods, traded in two stages, and we're going to have a J+1 real financial contracts. The prices of goods are going to be, at first, are going to lie on the positive reals of L+1 of 1 plus I, and we're going to have, on the other hand, prices for the financial contracts, and let's say there are going to be positive on the R of 1 plus J. I'm going to say positive because we're going to ask for the return to be strictly, or let's say non-negative, so the return of the contracts has to be positive. So in the general setting, the agent problem is going to be maximize a utility function that is going to depend only on the consumptions. And now I'm going to have a financial decision that I have to make, in the sense that I'm going to buy or sell contracts at the price Q at the first stage, and then I'm going to get a real return at the second stage given by this matrix D of psi that I'm going to get whenever I buy or whenever I sell. They said correctly. Okay. Well, whenever I buy or sell contracts. So the general setting is this. At the first stage, I have to make a decision of goods and contracts. And on the second stage, I'm going to have the same goods or same consumption. And I'm going to have a D1, D2, or DXI delivery on goods. So this is a real financial market, and we're going to try to solve this problem as an equilibrium problem with our Walrasian technology. We define the excess supply function as always as the difference between the available goods and the consumption, and we're going to. For this solution, I incorporate directly the non-arbitrage condition in the sense that I get a reduced form of the Walrasian just depending on the price P, which are going to be just, let's say, modified price that are going to lie in the non-arbitrage space. We are trying we try different solutions or different formulations for this Walrasian function. This is not the only one that works. This is not unique, of course. This is the one that I like because we pass from a equilibrium with goods and contracts to a modified equilibrium to the previous case. But still, you can define a Walrasian with excess supply on goods and on contracts. Let's say that this is the one that is working, incorporating directly the non-arbitrage condition. We solve it with this classical example Two agents, well, we have three agents, so two types. We have two goods, three possible stage, utility function be given by this nice concave function, and we have securities that are going to be just two securities for the three stages. So this market is incomplete, and we obtain really nice convergence properties for this problem. We are solving bigger examples for this case, but those are preliminaries by this time. So some references there are papers with Fan, with Joffre and Wetz, and Rockefeller and Wetz. And this is it. Thank you for your attention.